So thank you for joining us today. It's now my pleasure to introduce our speaker, Sushmita Kohli, PhD, Staff Scientist, Process Chromatography, R&D from Bio-Rad Laboratories.
Thank you for the kind introduction. I welcome all the viewers for attending this webinar. Today, I will be speaking about demonstrating modular selectivity with a weak anion exchange Higgs resin for achieving high map purity and recovery in a downstream purification process. I would like to start by introducing our newly launched product, the Nuvia W' 2A resin. This novel ligand presents a dual modality wherein it possesses the properties of a weak anion exchanger as well as a Higgs resin with a pKa of 7.4. Importantly, the selectivity of this resin can be modulated with changes made in the process conditions. That is, when operated at a pH near its pKa value of 7.4, the resin will possess an overall 50% charge state and therefore will demonstrate an equal anion exchanger and Higgs characteristics to it. While when operated at a pH below 6.4, the resin will possess an overall greater than 90% charge state and act more like an anion exchanger. On the other hand, at a pH above 8.4, the resin will predominantly be present with a greater than 90% uncharged state and act more like a Higgs adsorbent. With this background in place, we would like to demonstrate a use case for this resin for biotherapeutic purification. Traditionally, after a protein A capture step, polishing chromatography typically involves 2 to 4 orthogonal steps, which can be a combination of either anion exchange, cation exchange, or hydrophobic interaction chromatography. Although these traditionally operated single mode ion exchange chromatography methods have been employed extensively, but achieving high purity and yield have often been challenging for several molecules, including monoclonal antibodies, bispecific antibodies, and other recombinant proteins. To overcome these limitations, there has been a significant increase in the implementation of multimodal adsorbents, which not only help to reduce the number of steps, but also improve the overall process economics and achieve the sustainability goals. In our case study today, we will be demonstrating how Nuvia W' 2A was instrumental in removing aggregates from a protein A viral inactivated pool. Presented here in this slide is the study outline, which comprised of 5 steps, starting with characterizing a set of protein A pools for its aggregate content. Secondly, developing critical analytical methods which can provide quantitative values of aggregate clearance and monomer recovery. In this segment, we used SEC UPLC method and analytical protein A HPLC method. Next, a preliminary process condition screening was done to evaluate at what conditions the novel multimodal adsorbent can be operated in a flow-through mode to separate the aggregates from MAB monomers. Next, a DOE approach was employed to carry out a systematic process condition screening to map out and optimize the parameters for effective aggregate clearance as well as MAB monomer recovery. Finally, the results of the DOE study was utilized to validate the process parameters on a bench scale column. Starting with the first step, that is characterizing the protein A pools. In this study, we evaluated 7 different protein A pools obtained from a third-party vendor for determining its aggregate content. These protein A pools were viral inactivated at pH 3 for an hour and then neutralized to pH 5 as would be done in a typical platform protein A process. The neutralized viral inactivated pools were then analyzed using the SEC UPLC assay to calculate the aggregate percentages. From this study, we found that sample number 5 or custom human IgG1 kappa MAB was our molecule of choice for further experimental work. The next phase of the study workflow was to develop critical analytical methods. First, SEC-UPLC method was developed using a Waters SEC column for determining the MAB aggregates. The table on the right presents the analytical conditions which was developed with a runtime of 10 minutes per sample. The figure on the left shows an overlay of 10 replicate injections demonstrating good method reproducibility. Further, the repeatability test showed that less than 2% RSD value was obtained, which confirmed a robust test methodology. For the quantification of MAB monomer recovery, a protein A HPLC column was used to develop the assay on an Agilent system. Presented in the table on the left are the analytical conditions used for performing the assay, which was developed with a short run time of 4 minutes per sample. The third step was preliminary process condition screening for designing a flow-through process. As mentioned previously in the introductory slide, Nuvia W'2A resin has a ligand structure with a modulable selectivity. The structure consists of a weak anion exchanger group and a hydrophobic phenyl group. Depending on the process conditions utilized, the degree of its charged state can be altered. In the current study, the monoclonal antibody under consideration possessed a pI of 6.9. Therefore, at a pH around 5, both the ligand as well as the MAB monomer will possess a net positive charge, which will lead to the MAB monomer being collected in the flow-through fraction, while the aggregate will be bound to the resin due to its intrinsic hydrophobic character. With this approach in mind, we designed a comparative study to investigate resin's process capabilities. From the preliminary screening studies, we could find that the Nuvia W'2A resin performed better than the other two commercially available multimodal resins for clearing the high molecular weight impurities for the molecule under consideration, which was an IgG1 kappa mAb. After obtaining the requisite data from the preliminary process condition screening, we further wanted to map out and optimize the process parameters using a DOE approach in the fourth step. For the design of experiment studies or the DOE studies, we created a full factorial design with 2 factors and 3 levels. The 2 factors considered were pH and salt concentration. The pH were altered at 3 levels, that is at pH 5, 6.5, and 8, while the salt concentration were altered at 3 levels, that is 100, 300, and 500 millimolar sodium chloride concentration. With 2 replicates, there were a total of 18 experiments, and the output parameters analyzed were aggregate clearance and MAB monomer recovery. The present slide shows the workflow utilized to perform the DOE studies in a 96-well format. This was done by opting a high throughput screening approach to minimize the time, effort, and material cost used to perform these experiments. As a first step, 40 microliter of the Nuvia W'2A resin was dispensed in each well and was equilibrated with the appropriate buffer composition. Next, the equilibrated resin bed was loaded with the neutralized, viral inactivated, and buffer exchanged MAP pools. The resin load challenge at this step was maintained at 50 milligrams of protein per ml of resin. The flow-through fractions were collected in a separate collection plate. For the wash step, the resin bed was washed with the equilibration buffer and the unbound fractions were collected. Finally, the plate with the resin was regenerated using a 0.1 molar citrate buffer. The results of the DOE analysis is presented in this slide. The top left plot shows the overlaid contour plots of the two responses, that is, high molecular weight clearance and MAB monomer recovery as a function of pH and salt concentration. The overlapped white area shows the desired optima. Additionally, the plot on the right shows the one with the response optimizer. The software predicted optima were found to be at pH 8, and 221 millimolar sodium chloride concentration for maximizing the high molecular weight clearance and monomer recovery. Finally, after obtaining the optimized process conditions, we wanted to validate it from the batch scale to the bench scale column format. This slide shows the purification protocol that was employed on the column for separating the MAB monomers from the aggregates in a flow-through mode. A 0.5 ml column was packed with the Nuvia W'2A resin, which was operated at a flow rate at 76.5 centimeter per hour with a relatively short resistance time of 2 minutes. The table on the right shows the composition of the buffer used for the column study. The flow-through and the wash fractions were collected and pooled together during the purification run. These fractions were further analyzed by SEC-UPLC assay for aggregate content and by protein HPLC assay to determine the monomer recovery. From the SEC-UPLC analysis, we could observe that there was a significant reduction in the aggregate levels from 7.3% in the load to 0.7% in the flow-through fractions. This translated to almost a tenfold reduction or greater than 90% impurity clearance in a single step purification in the flow-through polishing step. Further, the protein HPLC assay confirmed that around 85% of the MAB monomer could be recovered in the pooled flow-through fractions. In conclusion, we can say that our recently launched product, Nuvia W'2A resin, could successfully demonstrate its process capability as a polishing step for separating MAB monomers from aggregates or higher molecular species in a flow-through mode. With flow-through mode of purification becoming an integral part of continuous manufacturing processes, this new multimodal anion exchange adsorbent can be used for process intensification purposes. Thirdly, the DOE approach helped to obtain the optimal process conditions for maximizing both monomer recovery as well as aggregate clearance. The preparative column run validated the DOE predictions since the flow-through pools did corroborate well with the expected aggregate clearance levels. Overall, the purified flow-through fractions achieved the typical specification criteria of being lesser than 1% aggregate with 85% monomer recovery. Thank you for your time and kind attention for today's webcast. Please do visit our digital resource site for receiving samples of this new resin. With that, I welcome any questions from the audience.
Okay, great. And as a reminder to our audience, you can go ahead and type in your questions for our speaker now. So our first question is, you used SEC-UPLC to analyze aggregates. Are there other methods to monitor aggregates?
Yes, there are other methods to monitor aggregates like gel electrophoresis based ones, but these are low throughput and mostly provide qualitative or a semi-quantitative analysis, whereas SEC UPLC is a high throughput method and it's a robust method to quantify and analyze aggregate content.
Okay, and our next question is, how do you measure the level of a molecule's hydrophobicity?
Yeah, so for measuring the level of a molecule's hydrophobicity, one can carry out like experimentally Higgs chromatography to determine the relative hydrophobic index. Other bioinformatic tools can also be used, like using the Mo software to calculate the hydrophobic patches and evaluate its SAP maps.
And is this resin base stable?
Yes, that's a good question. The resin is a base stable resin which has been evaluated for its stability up to 100 cycles. And it has also been observed to perform consistently with minimal changes to its DBC or protein recovery values.
All right, well, it looks like we're running just a bit short on time, so if we don't get to your questions, we'll be passing them along to Sushmita, who can follow up with you directly. So please go ahead and continue to type in any questions you have, and we'll get those passed along. The last question for the webcast is, how is it different from other anion exchange mixed mode resins?
This Nuvia W prime 2A resin is a mixed mode resin which has a weak anion exchanger group in it, and its charge state can be modulated with changes in the process conditions. Whereas other mixed mode anion exchanger resins, they normally have a quaternary amine group whose charge remains constant and it cannot be modulated within the working pH range. So that is what sets this particular product apart from others.
All right. Well, thank you so much, Susmita.